Hello friends, today's question. A block of mass m with a semicircular track of radius r rests on a horizontal frictionless surface. A uniform cylinder of radius small r and mass small m is released from rest at the top point A. The cylinder slips on a semicircular frictionless track. How far has the block moved when the cylinder reaches the bottom point B of the track? And how fast is the block moving when the cylinder reaches the bottom of the track? So we have a block of mass capital M and a cylinder of small m, mass m, and it is moving from point A to point B, and it is asked that when this semicircular cylinder reaches point B, we have to find out two things: how much is the distance traveled by the cylinder, and how far the block, and what is the, we can say, velocity of the block. So in this case, let us first of all find out in which direction the block as well as the cylinder will be moving. So as it is a semicircular surface, so the normal will be acting in this direction, and this normal can be divided into two components. So we have nx and ny. So because of this nx component, the block will be moving towards left. Okay, so we can say, and this is the point of contact between your block as well as the cylinder. So we can say, because of the due to nx, block M will move towards left, and we say, let its velocity be v1. With velocity v1, and the cylinder M moves along the curved path with velocity v2. With velocity v2. Okay. So this, let me draw it here. So we have this curved path, and the cylinder starts from point A, and this is the lowest point B. So it travels like this and reaches this point B, and its radius is given as small r. So we can say this distance will be equal to r minus small r, and v2 will be the velocity of this cylinder, and v1 with the velocity of the block. So as there is no external force, in the absence of external force, in the absence of external force, the momentum will be conserved. Will be conserved. So we can say that our m into V2 is equal to capital M multiplied by V1, and from here we can find out our V1, that V1 is equal to m upon capital M multiplied by V2. So let this be question number 1. And now we can use the conservation of energy. Okay. So you can say by conservation of energy, the loss of potential energy for the cylinder, loss of potential energy of cylinder having mass small m will be equal to gain in the kinetic energy of block capital M plus gain in the kinetic energy of cylinder small m. So loss in the kinetic energy is our mg, and the height it falls is r minus r is equal to half m v1 square plus half m v2 square. And we already know the relationship between v1 and v2 from equation 1. So we can say, using equation 1, v1 is equal to m divided by capital M multiplied by v2. And we can write this as mg r minus r is equal to half m, and we get m multiplied divided by capital M v2 whole square plus half m v2 square. And if we open the bracket, we can write this will be equal to mg r minus r is equal to half, we get m square v2 square m square plus half m v2 square. And this goes with this, and we can cancel this m. So this will go to g r minus r is equal to half m v2 square divided by capital M plus half v2 square. We can solve it further, is equal to, we can take half v2 square as common, and we are left with m capital M plus 1. So from here we can say that our v2 square is equal to, this will be coming as 2g r minus small r and divided by 1 plus m plus capital M. Okay, and from here we get that our v2 is square root of 2g r minus capital R, small r rather, and 1 plus m. Now this is the velocity of the, you can say, cylinder, but we are supposed to find out velocity of the block. Okay, how fast the block moving when the cylinder, yeah. So we are going to use equation 1. Using equation 1, we can say that V1 is equal to m divided by m, and this comes equal to 2g r minus small r divided by, and we get this as 1 plus m. So we can write it here that V1, or rather we can say, if we take m inside the bracket, so we get this as V1 is equal to m, this will be 2g r minus r, and we get m square, taking m as LCM, and this cancel out with this, so we get V1 is equal to m square root of 2g r minus r divided by m capital M plus small m. So this is our velocity of the block. This is the velocity of the block m when cylinder small m reaches point B. This completes our one of the part, rather B part, and we can also write for the, you can say, A part, but it asks how far the block is moved. Okay. So in this case also, in the absence of the external force, okay, so there is no external force, you can say, in the absence of external force, the center of mass which will be written as COM of the system will not get displaced, Okay. Or we can say that delta x cm will be equal to 0. So once again, let us draw the diagram. So this is point A, and this is B. This is moving with the velocity of V1, velocity of V2 in this direction. Okay, and let us suppose that we assume that towards right is our positive x-axis. So this is positive x-axis, and towards left we say that this is our negative x-axis. Okay. So when the cylinder reaches point B, when cylinder M reaches point B, the displacement of the block capital M will be along negative x-axis. Okay, will be along negative x-axis, and let us say and we say negative x-axis let it be x1 with respect to ground. Okay. With respect to ground. So from here we can say that change of the block with respect to ground is equal to, let us suppose, delta x1, and this will be equal to minus of x1. And similarly we can say the center of mass for the cylinder M its displacement is along positive x-axis, and we can say relative to the block, is delta x of the cylinder with respect to block is equal to r minus small r. Okay. Therefore, with respect to ground, the displacement of center of mass, let us suppose, is delta x2, and we can say that delta x2 will be equal to delta xb plus delta xbg, and we get that delta x2 is r minus r, and this will be minus of x1. And next we are going to use the formula for the displacement of the center of the mass. Okay. So we can say, according to the displacement of center of mass, delta x cm is equal to m1 delta x1 plus m2 delta x2 divided by m1 plus m2. Now in this case, our m1 is the capital M, that is block, and m2 is the small m, that is our cylinder. So if we substitute the value as the center of mass, we already said that there will be no displacement, so delta xcm is 0. We can say that delta xcm is 0, so 0 is equal to m1 is capital M, and we already know delta x1 is minus of x1 plus this is small m, and delta of x2 is r minus of x1 divided by m plus small m. From here we can say that we can open this bracket and take x1 as common here and here as well. So we get this as x1 is m plus small m is equal to m r minus r. So we get the displacement, that is x1, is equal to m r minus small r divided by m plus small m. So this is our displacement of the block. This is the displacement of the block capital M when the cylinder reaches point B, that is the bottom. When cylinder M reaches point B, that is the bottom of the track. Bottom of the track. So this completes the question. Thank you.